We're going to take a look at how the neuron communicates with the skeletal muscle cell. We'll probably revisit this when we talk about the skeletal muscle, but I want to go over it here as we talk about the nervous system, because those synapses are, of course, part of the nervous system. So if we go back up here really quickly and take a look at these frog toe-like structures that I talked about, shown here. Okay, notice their flattened surface. If we keep that in mind as we go down here and look at what we see here, here's my frog toe. Okay, so here's my frog toe. Okay, and that is, of course, it's cut. We're sectioning the skeletal muscle transversely, the muscle fiber, I should say, and so we're sectioning the synapse as well, right? So we're looking into it from a transverse section. And if we look at that and zoom in on this, what you're going to see, let me explain a little bit of what you're looking at here. Recall that skeletal muscle fibers are single cells, but when you dive into those cells, there are fibers bundled up inside the cells made out of connective tissue, cytoskeletal proteins. And so you actually can see these are the little these little bundles shown here that are going to generate the force of contraction. So I want you to see those there. Okay. And you can see that they're spread throughout, and so cytoplasm would be found around it. Okay. There's also going to be an abundance of mitochondria in the skeletal muscle and in the nerve ending as well. So zooming closer, right? Let's look at closer. If we look at this nerve, there are folds within the nerve ending, the synaptic ending, and those folds, of course, are going to increase the surface area, right? They are matched on the other side of the muscle fiber, in the muscle fiber, by a region that is also heavily folded. So let's look at that. You can see, I'll outline the neuron. So here's my neuron, I'm outlining it in green. Notice all of my mitochondria, because I'm going to need a lot of ATP in that motor neuron. Notice also my synaptic vesicles, right? So each of these are my synaptic vesicles, and those are going to be containing neurotransmitter. Every single somatic motor neuron, everywhere, always, releases the neurotransmitter acetylcholine. Okay? So that is a neurotransmitter. The neurotransmitter is acetylcholine. Okay? Which is abbreviated ACTH. Always acetylcholine. Here I'm going to highlight in pink. That's not a good choice in colors. Let's try a different pink, or purple. I guess we'll do this pink. The other side of the synapse. So this is a case where we've got a synapse that is synapsing into a non-neural cell. But the area that I'm now coloring in pink is what we call our motor end plate, and it's heavily folded like so. Okay? And so you can see that we've got a tremendous amount of surface area dedicated to the synapse, to this region in the synapse. And if you were to look up here, you would see motor end plates found here and a little bit off picture here, from that interesting frog toe-like synaptic ending. This, okay, and so I want you to kind of keep that in mind. We call this together, the motor neuron plus the motor end plate of the skeletal muscle, we call that our neuromuscular junction. Okay, that's our neuromuscular junction. The synaptic cleft, by the way, Okay, is this space that's in between here, and so this is the area where the neurotransmitter, we're going to release that neurotransmitter into that area and allow it to diffuse into this synaptic cleft. All right. Now, we're going to walk you through, I'm going to walk you through the process of synaptic transmission. Okay. And I'll start with a quick reminder of the steps involved in the neuron itself. Okay. So we're going to remember, in fact, let me go ahead and open up a new slide here, because I want to remind you quickly of how a synapse works. We've walked through this before, but when the action potential arrives at the synaptic terminal, okay, and in the past I've drawn the synaptic terminal like this, but now we'll draw it so it looks like the frog toe. Okay, and so we've got these little toe-like structures like so. Okay, and when the action potential arrives at that synapse, the synaptic terminal, we're going to have that action potential change the membrane potential of the synapse. So this membrane here that I'm trying to color in green, not very successfully, is going to be depolarized, right, by that action potential. And when it's depolarized, that will cause the opening of these voltage-gated calcium channels. And I'm not going to draw the channels in, we're just going to shorthand this so that it's quick and easy. And calcium is going to enter into the synapse, which will further depolarize the synapse. But more importantly, those synaptic vesicles filled with neurotransmitters, okay, at the surface of the cell membrane are going to be docked, right? You remember me talking about these docking proteins. So they're going to be held in place by these docking proteins. And when calcium binds to these docking proteins, so let's throw a calcium in right here, okay, then that will spring the trap, so to speak. Whoops, wrong way of doing that. And we end up with this release of neurotransmitter into the synaptic cleft. And so again, that neurotransmitter is going to be acetylcholine. So now we'll fill this synaptic cleft with acetylcholine. And you'll recall, if you will, that acetylcholine will then activate receptors on the postsynaptic membrane, and that will trigger a graded potential in the postsynaptic cell. And then also recall that acetylcholine is destroyed. We've gone through this, so this is all review. Acetylcholine is destroyed by the enzyme acetylcholine esterase. And if you're thinking, when did we go through this? I don't remember in this. This is all like Greek to me. Go back to the neurons and synapses lecture. We did walk through this, okay? And so acetylcholine will be destroyed in acetylcholine esterase, and it will be chomped up to produce choline and acetate. Neither of those are effective neurotransmitters, and the choline will be recycled back into the neuron to be recombined with acetyl-CoA, right, to give us acetylcholine once more. That's the basics there. Now this exact same process is going to occur at the motor neuromuscular junction. This blue line here would represent the membrane of the skeletal muscle fiber. Now, quick note on vocabulary. When we're dealing with skeletal muscle, when we're dealing with muscle in general, we tend to use sarco. Okay, that terminology means muscle. And so in most cells, I would talk about the cell membrane, or another term for the cell membrane is plasmolemma. But in skeletal muscle, that plasma membrane is actually called the sarcolemma. And then likewise, the endoplasmic reticulum in the skeletal muscle is called the Sarcoplasmic Reticulum. And the cytoplasm is called the sarcoplasm. Okay, and so forth. So be comfortable with that terminology because I will often use those phrases. Now we're going to take a look at my diagram here, and I'm going to walk you through this step by step, and it's going to seem, what I normally do is I draw this out on the board, but then I decided to get industrious and draw this in a PowerPoint slide that we could then flip through each area. So let's take a look at this together. And I'm going to highlight, let's make sure I'm on my smallest little highlighter here, some of the players here. This would be the skeletal muscle fiber. So this is my skeletal muscle. Okay, this is my skeletal muscle. Not shown here, but I can even kind of sketch it in, is we are going to have some actin and myosin fibers throughout my skeletal muscle fiber. Okay, so actin and myosin are components of the cell membrane, and they would be these overlapping fibers. We will get into the specifics of this later. I'm just going to go ahead and sketch these in really quickly, just to remind you of their presence, so that when we do move on to the skeletal muscle, you'll be able to think back to this and kind of put everything in place. So my plasma membrane of my skeletal muscle fiber, my sarcolemma, if you will, is this structure that I'm going to highlight here really quickly in green. Each of these folds would represent the folds of the motor end plate. To state what I hope is obvious is this is not meant in any way to be anatomically accurate. This is strictly symbolic. Now as you follow my green line here, watch me as I draw down. What I'm doing is I'm following the sarcolemma as it plunges into the internal, or plunges deep into the middle of the skeletal muscle cell. Now importantly, the extracellular fluid, let me make sure you notice that. The extracellular fluid is in this tube. Do you see this? All of this pink area is extracellular fluid, and all of this pink area out here is extracellular fluid. Notice my extracellular fluid there as well. So imagine everything's pink there. That's critical to understand. And this invagination, that's essentially what this is, it's an invagination, a fold that goes very, very deep, is what we call our T-tubule. And that T-tubule is very closely associated to our, we'll try that color, Sarcoplasmic Reticulum. So now you're following my purplish, pale purplish line, and you can see here that I've drawn this little squiggly shape to represent my Sarcoplasmic Reticulum. And notice that there's a Sarcoplasmic Reticulum on both sides of that T-tubule. Okay. We actually would refer to this as the triad, or the terminal cisternae. And it involves two Sarcoplasmic Reticulum kissing that T-tubule. Okay, so this arrangement right there. Let's identify some other players in this diagram before we move on. And so here I want you to see that we're going to go back to the Let's highlight this one. This is my neuron, and you can see that this is my neuron plasma membrane there. Okay, and this is my synaptic terminal. Notice I have synaptic vesicles in there, and notice that these synaptic vesicles contain the neurotransmitter acetylcholine. As I mentioned, that's always true about skeletal muscle, about somatic motor neurons. It's always acetylcholine. Now I want to draw your attention to the little dudes in the, that'll work, in the synaptic cleft. These little Pac-Man guys are my acetylcholine esterase, okay? And they're going to hang out in the synaptic cleft and they're ready to go, okay? So in this condition, my muscle fiber is not contracting, and honestly my neuron is not being stimulated, so nothing's really happening. The muscle is at rest. There's always a little bit of muscle tone, so it's not completely limp or flaccid, but it's essentially in its resting state. Now I need to identify some other players. I almost forgot, that would have been tragic. I want you to see these here, okay? These little ion channels that I've drawn in green, and I kind of colored over them so it's hard to see them. We can even erase a little spot so you can see them a little better. Those ion channels that I've drawn in green are ligand gated, and specifically they are ligand gated, their ligand is acetylcholine, so we would call these acetylcholine receptors, and they open when acetylcholine binds to them. They have another name, and I want you to know this other name. That name is the nicotinic receptor. And it is named because it actually does in fact bind nicotine. Nicotine doesn't have as big of a role to play in skeletal muscle, but there are also nicotinic receptors in the brain, and when you inhale nicotine or consume nicotine in a gum or what have you, that nicotine does in fact activate the nicotinic acetylcholine receptors in the brain, which is one of the reasons why the nicotine relaxes us and helps us to feel more alert. These yellow and blue receptors that you can see right next door, so let me kind of look at those for you, and we'll circle them so you can see them. I'll circle them. Here's my yellow one, here's my blue one, and notice that they're not in the synapse. So this part right here, come on, is my neuromuscular junction. It includes the neuron and the motor end plate, right? So the motor end plate is where we see our nicotinic receptors. But this next part over here is not part of the synapse. Nevertheless, look at these channels right here. These are ion channels, and specifically, very important to understand and to realize and to see, these are voltage gated. Voltage gated sodium channels and voltage gated potassium channels. Where have you seen those before? In a neuron. Skeletal muscle cells are electrical cells just like neurons. They have a different function. The neuron is involved in transmitting information, but the skeletal muscle cell is involved in contraction. Nevertheless, contraction is regulated by a change in voltage. So now let's walk through the process, and this is going to be a little bit longish, but if we walk through this process, we're going to see how this works. Moving on to the next cell, we're going to begin with an action potential. So here's my action potential. It's going to travel down the axon into my synapse, and it will depolarize that membrane, right? It's going to depolarize the membrane potential of the synaptic terminal. So everything depolarizes. Okay? And that depolarization is then going to open up. We take a look at this. It's going to open up my calcium channel. So I essentially did this, by the way, step by step. So each slide shows you a new step. Okay, so here's my calcium channels, and here's my calcium coming in, because that membrane has been depolarized. Once it repolarizes, those calcium channels will close. But now my calcium is going to initiate by binding to those docking proteins. I did not draw the docking proteins here because I really didn't have enough room, but it's going to bind to those docking proteins, and notice that it's going to cause the release of acetylcholine into my synaptic cleft. Let me kind of circle those and make them a little bit bigger so you can see them. I'm not going to do that with all of them. Okay. Now the moment my acetylcholine enters into my synaptic cleft, my acetylcholine esterase is going to start chewing on it. But some of it will actually make it to those nicotinic receptors. And did I miss something here? Or did I just click on this twice? Oh, yeah, okay. Some of that is going to bind to the nicotinic receptors here. And I didn't actually draw them in an open state, but we can actually imagine that they're going to open up as that acetylcholine binds to these nicotinic receptors, causing them to open. Now when they open, these nicotinic receptors are sodium channels. Sodium is going to flood through. Now I'm not being entirely completely honest with you. They're actually sodium/potassium channels. A little bit of potassium will in fact sneak out of these nicotinic receptors. But importantly, and I'll show you the action potential anyway, prior to this sodium, I'll put it over here, the resting membrane potential of a motor neuron, of a skeletal muscle fiber is pretty darn close to -90 or -85. It's in that ballpark. And so if I'm already at potassium's equilibrium potential, there's really not a lot of driving force to move potassium out. But the reality is potassium can in fact move through those channels. It just really doesn't, because we're pretty close to that equilibrium potential for potassium. The sodium that comes into this cell will generate an excitatory postsynaptic potential in this region here. Okay? Now, just like we see in other cells, there's no guarantee that that's going to reach threshold. Okay, so it could be sub-threshold. If we don't get enough acetylcholine released into that synaptic cleft, we're not going to get enough sodium into our sarcoplasm, and we're not going to get a big enough graded potential or excitatory postsynaptic potential. But if we assume that we've reached threshold, then what's going to happen is that we're going to depolarize the cell membrane enough that here in this region that is nearby, okay, this part here, we're going to get the opening of those voltage-gated sodium channels, and we're going to get the rapid depolarization of the cell. We'll then get the opening of, they inactivate, so they will inactivate, and then we'll get the opening of the voltage-gated potassium channels, and we'll get an action potential that is going to travel down this T tubule. Okay, down this T tubule. The action potential travels all the way down the T tubule until it reaches a special protein called the Dhp receptor. DHP stands for dihydropyridine. You do not need to memorize that. DHP is good enough, okay? Dhp receptor. Now this receptor is voltage sensitive. It's not a channel. It is however, a protein that changes conformation or shape in response to voltage. Okay, so when the membrane depolarizes, that channel, that Dhp receptor, will change shape. It'll physically change shape. And notice, so I changed from that round shape to my rectangle shape to, or my diamond shape, to illustrate my point. And when it physically changes shape, it is tethered, physically connected to another protein called the Rhianidine receptor. The Rhianidine receptor is in fact an ion channel. And so when the DHP changes shape, it opens the Rhianidine receptor. When the Rhianidine receptor opens, it's going to allow, now I want to remind you that when we're dealing with concentration of ions, calcium is concentrated in the extracellular fluid, a whole bunch of it in the extracellular fluid. It's very, very, very low normally in the sarcoplasm, but it's also normally high in the Sarcoplasmic Reticulum. So we say that calcium is sequestered in the Sarcoplasmic Reticulum. So when that Rhianidine receptor opens up, calcium escapes from the Sarcoplasmic Reticulum, and so my calcium level in the cytoplasm steadily increases. And so you can see my calcium building up here in the sarcoplasm, increasing like so. Now, why do we care about that? Well, if you go back up here, just quickly, let's flip all the way back up here to these contractile fibers. There's a protein on these fibers that actually sense the presence of calcium. And so when calcium binds to that protein, and I will get into this mechanism, I promise I will teach you this, and you'll be like, that's a lot to learn. But calcium is going to bind to these proteins in this sarcomer, and that's going to allow muscle contraction. And so the muscle fiber will shorten as those sarcomers shorten, which gives us our contraction. And that's why the calcium matters as calcium comes out. Now, meanwhile, I actually named the protein troponin. We'll come back to that. Don't worry too much about troponin right now. Okay, but that's the name of the protein found in the sarcomer that's going to bind calcium. It's a calcium sensing protein. And once it binds to troponin, we're going to get muscle contraction. Okay. Meanwhile, while all of this is happening, this is a simultaneous thing, okay? While all of this is happening, my acetylcholine esterase here is chewing up my acetylcholine. So those nicotinic receptors don't stay open forever. Once acetylcholine in the synapse is gone, okay, once it's gone, those nicotinic receptors close. And once those nicotinic receptors are closed, the graded potential fades away, and the depolarizing stimuli that was causing those voltage-gated sodium channels to open disappears. Okay? And so what that ends up doing is allowing my DHP receptor right here to return to my resting state. Remember that it changes shape in response to depolarization of the membrane. If the membrane's not depolarized, it's going to change again back to its resting state, and that's going to cause the Rhianidine receptors to close. This works better on a PowerPoint where I'm clicking through it. But anywho, also at the same time, please understand this is all simultaneous. Okay, all of this is simultaneous. We have these receptors are actually transporters found in the sarcoplasmic reticulum, and they're called calcium ATPases. And what these calcium ATPases do is burn ATP. They chew through ATP to move calcium out of the cytoplasm back into the sarcoplasm. Now, when we're back up at this state, okay, with my Rhianidine receptors wide open, even though, yes, Okay, every time calcium encounters this receptor, it's pumped back in. It's like trying to put the, I guess whatever analogy, cows into the pasture or lock them in the corral when the gate on the other side is wide open. You're not going to be successful because that calcium's just going to go like, whoop, bye-bye, right? But when the Rhianidine receptor is closed, then gate's closed, so you can put those cows back into their pen, their holding pen, and they're going to stay because there's no way for them to get out. Okay? And so even though the ATPase is constantly working, it doesn't win this race. It can't corral the cows until the Rhianidine receptor has closed. But once calcium is removed from the cytoplasm, the muscle is going to actually return to its normal resting state. You're going to want to practice and go through the this entire process carefully. Like I said, I will revisit it when we get to the skeletal muscle, but I'm not going to spend as much time on it. I want you to know step by step and practice drawing it in whatever way works best for you to look at this and to understand this. Now, last slide, as I mentioned, we're going to be getting an action potential here, right? That's what actually occurs when we get our graded potential here. We get the opening of this action, or the generation of an action potential in the sarcolemma of the skeletal muscle fiber. Okay? Let's look at that action potential. I mentioned this to explain why potassium usually doesn't leave in abundance through the nicotinic receptor. Here we see a side-by-side comparison and contrast for my action potentials in my motor neuron versus my skeletal muscle. And in the motor neuron, we're going to have, it's not the greatest drawing in the world, but we do in fact have a hyperpolarization phase, this little phase right here. See, I should probably like redraw that. Let's kind of fix this because it's not very obvious. Okay. So we've got our hyperpolarization phase, and just like all the neurons have, it's looking pretty typical. We've got our resting membrane potential, our rising phase, our repolarization phase, all of the same processes that you've been taught. So sodium enters into the cell here, so I'd say this is sodium influx. The voltage-gated sodium channel deactivates here, so we've got inactivation of the voltage-gated sodium channel. And we've got the opening of the potassium channel, so we've got potassium influx here. And then we've got a continued movement of potassium out to give a MI hyperpolarization phase. Okay. Fairly standard action potential. Okay. Skeletal muscle is different. The biggest difference is that skeletal muscle starts down here at -90 or -85. Really depends on your textbook which one it is, but essentially you can round up -85 to -90, and that is pretty darn close to the potassium equilibrium potential. Remember, we talked about that. So the equilibrium potential for potassium is equal to approximately -90 millivolts. And so we're at that equilibrium potential. And so that kind of explains why, even though it is physically possible for potassium to escape through the nicotinic receptor, it doesn't really. At least not at first. More of it will escape once we start to depolarize the membrane. And then now let's look over here on this side. Here's my falling phase. Okay, so the whole thing. So here we've got the voltage-gated sodium channels opening up. At the peak, those voltage-gated sodium channels inactivate. My voltage-gated potassium channels are open, now maximally open, and potassium enters my cell. But there's no hyperpolarization phase because my resting membrane potential is right back there at the equilibrium potential of this cell. So we don't have a hyperpolarization phase. We do have a bit of a slowdown. And this slowdown is due to the simple fact that the closer we get to that equilibrium potential, the less likely potassium is to move. It certainly will still have a net efflux. Sorry, this should say efflux. Efflux meaning to move outside. Okay. But it's going to be less extreme of a driving force the closer we get to the equilibrium potential. Okay. There you go. All right. So I hope that makes sense to you.